Okay, well, welcome back after lunch. We have an exciting session here after lunch because everyone gets a little drowsy after you eat, right? So make sure everyone's excited about the afternoon. So we're going to kick it off with our students. You can see we've got 12 students over here who are competing in the poster competition tonight. And they're going to give you 3-minute elevator pitches on what their posters are about. So hopefully we'll create some excitement for you to come and ask them lots of difficult questions tonight. So this is, I think, one of the most fun parts of the workshop here is getting to see what the students are doing. I've done some of these 3-minute events with faculty members, and let me tell you, that's a mess. These students are going to be a lot better than faculty members at talking for only 3 minutes. So I'm looking forward to this. I will be timing. So I'm going to give them the hook at 3 minutes, and we'll move on to the next person. So with that, we'll start. One up.
So, hello, my name is Evan Bozek. I'm co-advised by Dr. Parisa Shkui and Dr. Jacques Riviere. So what I'm going to be presenting on is the contact and non-contact nonlinear resonance ultrasonic spectroscopy, or NRUS, for additively manufactured in raw samples. So NRUS is a material characterization method. It measures the hysteretic nonlinearity of a material, which basically means how the resonance frequency will change as you excite it at higher and higher amplitudes. So what you'll see is at high amplitudes, resonance frequency will actually decrease. And that can be indicative of several things, such as microcracks and different microstructural features, such as dislocations. So previously, the hysteretic nonlinearity has been correlated to fatigue life in some powder bed fusion samples. They were Ti-64. So it shows some promise, except there was some scatter in the nonlinear data due to the bonding between the sample and a piezoelectric disc, which is typically used to excite the sample. So what we're looking to do is to use an entirely non-contact excitation method with an air-coupled transducer. So what this does is you don't need to, well, you still need to repeat the experiment, of course, but there's no variability between one test and the next by bonding and rebonding the sample to the disc, which creates a lot of scatter in the nonlinear data. So what we're hoping to see is some differences between some heat-treated and AM, or some heat-treated AM and raw samples for our nonlinear measurements when we use, when we use an air-coupled transducer instead. So in general, what we're finding is that for the linear measurements, the air-coupled transducer works really well. There's not a lot of scatter in the data, as you can see on the right there. And in general, as we saw in previous studies for our nonlinear measurements, you can still measure it, but there's still quite a bit of scatter, which makes it a little difficult to tell between some of the heat treatments and manufacturing types. And the main difficulty with using air-coupled transducer as an excitation source is the amplitude is very, very low. So it doesn't excite the sample very much, which makes it difficult to see nonlinear effects at such low strain levels. So if you're interested in learning about more, I'll expand on some of the details of what we tried at the poster session later tonight. Thank you very much.
All right. Hello, my name is John Case. I am currently a 4th-year PhD student in the graduate program in acoustics. I'm actually planning on presenting this work in my master's thesis on Monday morning at 8:30 a.m. in ASB. So a little unofficial invitation if you all want to see a lot more on this. But today I'd like to introduce my poster on the photoacoustic measurement of the optical absorption of aerosols. So atmospheric aerosols typically consist of organic and natural sources of black carbon from like wildfires and things along those lines. Minerals such as sand and clay and oceanic and marine. These can cause big issues in two seemingly unrelated fields, the first being in climate forcing, and the second being in high energy light propagation. In high energy light propagation, an effect called thermal blooming occurs, in which local heating of air causes changes in the index of refraction, which can cause laser beams to diverge and lose intensity. So therefore, we used a photoacoustic method to develop a system to measure absorption due to aerosols natively. We employ a double-necked Helmholtz resonator, which is outlined in blue and yellow. And we have two acoustic inlet and outlet mufflers, as well as an acoustic enclosure to mitigate noise within our system. And some examples, one example of some of the data that we've taken with black carbon is shown in the plot on the top left. We currently have only done measurements with black carbon, but we soon plan to do measurements with wet aerosols, including a copper sulfate solution and sodium chloride solutions to mimic oceanic aerosols. And with that, I'd encourage everyone to come stop on my poster if you want to learn more later. Thank you.
Hello, I'm Shubham. I work in Dr. Kotapalli's lab. So the previous, something happened to the slide. Not entirely sure. Oh, that's weird. Oh, right. That's great. Yeah, that's great. Cool. So, oops. Yeah. So, So in the previous two presentations, we saw that both the transducers were opaque, right? So. That's one of the main problems with ultrasound transducers, actually when you want to integrate them with optical imaging technologies, that they're opaque. So to overcome this, we sort of developed these transparent ultrasound transducer devices. In essence, these devices are piezoelectric materials such as lithium niobate and PMNPT, coated with ITO and sandwiched between a transparent matching and backing layer. These devices further provide us the flexibility to be used in a single element or an array form. Consequently, we can use them for multiple applications. For imaging purposes, we implanted them over a mice brain as a cranial window, and we were able to do traditional neuroimaging such as intrinsic optical signal imaging and 2-photon. And what is interesting is that the cranial window that was implanted on the mice itself could be used as an ultrasound receiver. So you can do photoacoustic imaging with them. And those top two images are the photoacoustic images that we generated from a cranial window. They can not only receive sound, they can also transmit sound. So we can use them for ultrasound stimulation purposes. And so we plated some cells on them and we sent in ultrasound waves, and we can image through the transducers, and we can see actually the cells being stimulated through calcium imaging in the image below. And lastly, we also did them in an array form factor. As you can see that we are able to do ultrasound imaging with TOT array. We are able to do photoacoustic imaging with the same array, and we can also do Doppler ultrasound. So this opens up a lot of applications. We can use them in cancer and stem cell research. We can also do an awake mice neuroimaging, and they open a whole set of avenues for multi-scale biomedical imaging and stimulation applications. We have a detailed poster in the evening. You're more than welcome to visit. Thank you.
Hi, thanks for coming today. My name is Chang, a third-year PhD student in mechanical engineering, working with Dr. Lan and Dr. Smith. I'm very excited and glad to show our work, thrust damping, burst control, and vibration damping with wingtip electric top water. As you know, vibrations from periodic aerodynamic forces are one of the problems in the water aircraft. So passive and active damping methods has been researched. However, it requires additional or specialized actuator or devices to be installed, which increases weight, cost, energy consumption, and complexity. Here we introduce electric motor torque actuation in eVTOL. Idea is that we use the electric motor torque from motor to damp the vibration, which is usually used for thrust control on the wing. The torque applied to the rotor gives reaction torque to the flexible structure or the wing. In this video, you can see two cases which show vibration control off at the top, which is blue line, and control on at the bottom, red line. The first plot describes for the motor speed, which tells us that the thrust doesn't change much during vibration control. Second plot shows the beam deflection with control on the red line. It's much faster than without control blue line. Finally, we have the current input from the motor, which is linearly proportional to the torque. One thing I'd like to mention is that the torque at the third plot fluctuates much more than thrust's variation at the first plot, which describes that it is possible to use the vibration damping during thrust control. I'd like to introduce more about this since we don't have enough time. I hope we see in the poster session at night. Thank you very much.
Hello, everyone. My name is Ling Gao. I'm a fifth-year PhD student in the ESM department, and my advisor is Dr. Jack Riviere. So the goal of our study focus on the microphysical mechanisms behind the nonlinear elastic response of granular media. So we focus on study the effect of relative humidity and grain angularity on the nonlinear elastic responses. So we conducted experiments on the spherical glass bead and angular sand particles. The method we use is called the dynamic acoustoelastic testing. It can retrieve the nonlinear responses and thereby providing the observations on the elastic softening or weakening and some hysteresis phenomena too. We found that the nonlinear responses in the glass bead samples increases greatly with relative humidity, but we see very little dependence in sand particles. We hypothesize that this is related to the water absorption, which caused the weakening of the contact junctions. So in the sand particles, we expect that the angularity could hinder the weakening of contact junction, thereby hinders the opening or closing or the shearing, sliding between grains. So yeah, so if this has broad implications in nonlinear, the non-destructive evaluations and geophysics studies and other areas too. So if you're interested, please come to my poster tonight. Thank you.
Hi, everyone. My name is Prabhakaran Manogaran. I'm a fifth-year PhD student in Engineering, Science, and Mechanics Department. My advisor is Dr. Parisha Shukogi. So my poster is about dynamic acoustoelastic testing. My previous presenter was talking a bit about it. So what we do is basically the dynamic acoustoelastic testing is one of an advanced nonlinear acoustic technique, which is used to study the nonlinear elastic response of a solid medium. So basically, the way it works is you have a two dynamic field in which the low frequency pump wave will vibrate the sample so that it activates the nonlinearity of the test specimen. And then a high frequency probe wave will probe the changes that is happening in the test medium by measuring the wave velocity and then attenuation. So if you look at this in the literature, if you look, the DAET experiment is like predominantly performed in laboratory, and so we wanted to ease the application of this DAET test setup for field. So that's where we wanted to propose a modification for easing the applications. So what we do is we actually replace the low frequency pump that we use a piezoelectric disc to activate the test specimen. So we replace that mechanical strain pump by a thermal strain pump. So the figure over there shows the schematic representation of our proposed test setup. So can you go further? So this photograph, this shows the photograph of our experimental setup. So what we basically do is we have aluminum test specimen. In order to show the feasibility of this test setup, we are using an aluminum test specimen which has a close to fatigue crack. And we use angle beam wedge to generate Rayleigh surface wave on the surface of the test specimen. And for mechanical strain pump, we are replacing that with a thermal strain pump. So we have a hot air blower, which directly blows hot air on the surface of the sample. And in order to measure that temperature or the strain that is developed on the surface of the test specimen, we use a IR thermal camera. So one of the IR thermal camera image is shown over there too. So this is basically to show that the proposed test setup is actually working. And I also have one result without giving much of my results. So I also have like one result over there which shows the comparison between the evolution of wave velocity on the surface for an intact and then cracked specimen. We can clearly see that the drop in the wave velocity when a temperature is blown on the surface of the specimen, you can see that the drop in the wave velocity for a cracked region is larger than the intact region. And then what we do is we measure this drop for various locations along the crack and intact region and call it as a nonlinearity parameter gamma, and then show that this test setup can be actually used for characterizing close to fatigue crack. To the end, like we have developed a relatively simpler, inexpensive and portable DAT test setup, which I'll be talking more in my poster session. So if you're interested, please come and visit it. Yeah, thank you so much.
Hello, my name is Anna Morehouse. I am a second-year master's student in the graduate program at Penn State. This work that I'm introducing today seeks to solve the problem of noise radiation into the cabin rotorcraft from the airframe. And these airframe are made of composite carbon fiber laminates, which are very strong and lightweight, but in turn become very efficient noise radiators. Our proposed solution to this is to incorporate the acoustic black hole design into a composite stiffened panel. So this acoustic black hole is described by this taper with a layer of damping treatment shown at the top left. This is being incorporated into the profile of the stiffener and this ABH has been shown to reduce noise radiation while also removing material and decreasing mass. This is what we're moving forward with. And due to the novelty of the ABH, we are using a multi-objective evolutionary algorithm to explore the full design space of this application. This optimizer is seeking to minimize the noise radiation or vibration response mobility of the plate while also minimizing the cross-sectional area or the mass of the stiffener. So far, we are seeing slight but promising improvements shown in these mobility curves. And upon integration of these curves, you can see these objective values on the bottom right, and we are seeing this slight improvement so far. So if you have any curiosity or questions, I look forward to talking to you tonight. Thank you.
Hi, everyone. I'm Olivia, and I am a third-year PhD student working with Dr. Vijant in the Sound Perception and Pneumacoustics Laboratory. My project, my poster presentation is going to be on the assessment of cognitive effects of transportation noise on office workers with performance tasks and physiological data. Urban offices are nice in that there's this big space that you get to collaborate with all of your coworkers. However, this also means that you get to share all the noise that's coming from the outside and inside with all of your coworkers too. So my study is specifically focused on the transportation noise or the external noise that comes through the big windows that are often associated with open offices. We are using recorded transportation noise stimuli. So we're using road, rail, and subsonic aircraft, and these were recorded by a previous member in our lab. We will be reproducing these sound signals in our auralization facility, where we have 30 loudspeakers and 2 subwoofers. And while we have different stimuli being reproduced, we will have subjects do some cognitive tasks. And their performance will be measured with either reaction time or accuracy. We're also taking physiological measurements such as the EEG for brain activity, ECG for heart rate, and EDA for skin resistance to see the effects of transportational stimuli on their performance and their cognitive effects. And here are some sample results from these different physiological measures and the cognitive tasks. If you're curious, the overall goal of this study is to give better acoustic solutions to spaces such as open offices where noise can be a detrimental factor in one's cognition and performance. If you are curious about what these graphs mean, what we've done so far, what our next steps are, and how you can potentially be involved in this study, please come talk to me at the poster session later tonight. I hope to see you all there.
Hello, hello. How's everyone doing? My name is Raja Akif, Raja Zahiruddin. I'm a PhD student in aerospace engineering. So as you can see here is my poster. In vertical takeoff and landing vehicles currently, more and more has been employing the stack rotor configuration. So these are 2 rotors on top of each other, spinning in the same direction. So the main objective of my work is to describe the effects on in acoustics and flight performance when the azimuthal phase or the phase angle between the 2 blades are varied. So there's a theory that when you play around with the phase at certain angles, it will be quieter. So the second objective is for us to see what are the independent load measurements on these 2 rotors. So to achieve these 2 specific missions, right, a configuration that we used must be 2 motors mounted on top of each other that is not mechanically or physically connected by any means. So this configuration comes with a whole sweep of troubles, especially maintaining the RPM between the 2 rotors, because any slight change will then change your phase angle. So if you're interested in seeing the results and what we figured out in both acoustics and performance, visit us at the booth or contact me via email. Thank you.
Hello, everyone. My name is Ferdowsi Ronak. I'm a 3rd-year PhD student in the graduate program in acoustics, and I work in biomedical acoustics Simon Lab. So my poster we show our work on how elastic modulus and impurity affect acoustic cavitation in polyacrylamide hydrogels. So as we know, acoustic cavitation is utilized in therapeutic ultrasound to create beneficial bioeffects such as tumor ablation, drug delivery, or disruption of blood clots. But it is also cavitation is avoided in diagnostic ultrasound as it can cause unwanted tissue damage. So it is important to understand how tissue elasticity and the inhomogeneities commonly found in tissue may affect acoustic cavitation there. So for our study, we used 3 different levels of elastic modulus in tissue mimicking polyacrylamide hydrogels as shown in the first plot, and to see how increasing elastic modulus may affect bubble nuclei available for acoustic cavitation in these gels. And the central figure shows our experimental setup. We used a single element HIFU transducer to induce acoustic cavitation in these gels, in deionized and degassed water, of course. And we use a high-speed photography at 40,000 frames per second to observe these cavitation activities. So for the elastic modulus study, on the right side column shows when we increased or when we had high peak negative pressure, shock scattering was observed at our targeted frame, but with increasing elastic modulus, this shock scattering and bubble nuclei consistency, which is associated with this shock scattering, decreased. And for our impurity study, we first observed that for unaltered polyacrylamide gels, cavitation threshold, which is the peak negative pressure required to have cavitation 50% of the time, for unaltered polyacrylamide, cavitation threshold was the highest, as represented as the red dots in these plots. And when we introduced hydrophobic inhomogeneities or like impurities such as cholesterol crystals and bovine serum albumin in these polyacrylamide gels, these cavitation thresholds largely dropped, which means that hydrophobicity of impurities or like inhomogeneities found in a body has something to do or like plays a great role in reducing cavitation threshold. I will be happy to discuss more in the poster session. Thank you for your attention.
Good afternoon, everyone. My name is Lalit. I'm a third-year PhD student from the Engineering Science and Mechanics department. I work with Dr. Parisa Shekovi and Dr. Clifford Lissenden from the Penn State Ultrasonics Lab. My poster topic is on controlling surface waves in granular media using a metabarrier. Do you all know that despite the current advances in earthquake engineering, approximately 20,000 people die every year due to earthquakes? And surprisingly, there are over 50 active seismic zones right in California, with most of the residents living within 10 to 20 miles from the active zone. Therefore, controlling seismic waves that generate from the earthquakes is of utmost and critical importance to protect urbanized areas and civil infrastructures. Out of all the seismic waves, the most destructive one is the surface waves because they they have a larger amplitude. So how do we control the surface waves? And this is where my research comes in. In my research, we propose on designing a meta-barrier-based foundations to suppress these surface waves by taking them deeper into the half space. Meta-barriers can be thought of simply as a group of resonators that resonate upon an incident wave propagation so that we can manipulate the elastic wave as we want. Most of the meta-barrier configurations till date consider soil to be an isotropic media and design it based on that. In my research, we are taking a step forward by including the inhomogeneity of the granular media in designing a more realistic meta-barrier configurations to mitigate the surface wave propagation. If you're really more interested to know about the technical details of the meta-barriers and to know more about how they're performing in a real case scenario, I would like to take this opportunity to invite you all to my poster today evening. Thank you.
Hello, my name is Emma Shaw. I am a third-year master's student here in the graduate program of acoustics. My advisor is Dr. Vic Sparrow, and my research with him is funded by the FAA through Ascent Project 62. And I should say right now that even though FAA funds me, this is not their official findings. Anything I say here is my responsibility, not theirs. So my project with them is looking at the use of high fidelity weather data to improve noise propagation predictions. So the FAA has a program called the Aviation Environmental Design Tool that they use to predict noise propagation around airports resulting from aircraft operations such as arrivals and departures. But programs like these tend to use only one one set of average weather values to create adjustments, which we know that the real world is not homogeneous as they are assuming there. So we have been looking at using high fidelity weather data to specifically improve the calculation of the acoustic impedance adjustment in AEDT. And to your right, you can see a couple of visualizations that have been created of the acoustic impedance adjustment around the San Francisco airport using some high fidelity weather data that has been sourced from a company called Spire Global. And if you would like to know more about what we have found and what we think will come of this, please come talk to me. I'd be more than happy to talk to you about it tonight at my poster presentation.
Okay, thanks to all the students. That was terrific. A couple of notes on the poster competition tonight for those of you here in the audience and also online. We're going to ask our visitors to judge the posters, so please go around and talk to the students. Diane Beerley will have the forms for you to fill out, very easy to fill out. So I'll have those for you tonight at the exhibition. And then for our online participants, we also have an online poster evaluation process. And I think Kelly is going to walk us through how that works so you can see that. Here we go.
Okay, so everybody online should be able to hear me. I'm sorry, it's a little echoey for the people in the room. So those online, you're gonna go up to the Expo tab here. And then you can enter any booth, which is their poster. So I'm just gonna select this first one. And then I'm going to just kind of click around like I'm walking around on the screen. From here, you can view the full poster up here. You can also download the poster. So here you can see the last name, PDF, and you would just download that to view the poster. You can read the abstract as well. And all I'm doing is just clicking around on my screen, just like I'm walking around in a room. And so here's the poster, and you can just look there. Any questions from our online? Any questions from our online guests? Nope, I don't think so.
Okay, do we have audio? All right, excellent. Steve, are there any other announcements for tonight other than judging on the posters?
I'm trying to can you hear me now?
Yes.
No other announcements except I think we're opening up the judging to Penn State faculty who do not have students in the competition, just so we have enough judges.
Excellent. Thank you. Okay. Well, we're running a few minutes early, but that's okay. I'm the next person on the agenda, so I'll take more time.
I think Kelly's got to kick you out and then start a new session. Is that right, Kelly?
That is correct.
Okay. So everybody's got to get back in, unfortunately.
Okay.